Hi guys, we're back with the second video of Chapter 8. In the previous video we kind of discussed a little bit about the nature of metabolic reactions, chemical reactions. We discussed the first and second laws of thermodynamics and how they kind of govern these metabolic chemical reactions. And in today's video we're going to start to discuss a little bit more in terms of specifics of the energy that is kind of the central hub of these chemical reactions. Okay, one of the first things I want to discuss here is something known as Gibbs free energy, otherwise known as free energy. One of the things that biologists really want to know in terms of this micro scale biology, this cellular level scale biology, is which chemical reactions occur spontaneously and which ones are going to require input of energy. And so this is important because it allows scientists to understand which chemical reactions are going to be used for the cell to actually do work and which ones are going to which chemical reactions are going to have energy put into them to actually run or work. Okay? So this idea of free energy is something that describes energy that can do work. Okay, so this phenomenon known as Gibbs free energy describes a living system's free energy that is available to do work. Obviously, when temperature and pressure is uniform like that in the living cell. Okay, now one of the things that is expanded on greatly in the book, which we're not going to cover a lot of, if at all, and the College Board has even said that we don't need to cover this stuff in depth, is the equation for Gibbs free energy. The equation that you see in front of you describes this idea of free energy in mathematical terms, and this change in G is really what we're interested in. That's the thing that we're going to spend a lot of our time discussing. And we're going to leave out kind of this stuff here and how an interpretation of these factors of the formula lead us to understanding what the change in G is. Okay, what you really have to understand is that the change in free energy, or the energy that could eventually do work for a living cell, or the living cell could use to do work, is a function of the change in the enthalpy, a change in the total entropy. Okay, the change in the enthalpy, which is basically the total energy of the system, as well as the change of the entropy. Okay, and so the change in the total energy is not necessarily difficult to measure, but the change in entropy sometimes can be. Okay, regardless, we don't need to know a whole lot about it other than the fact that these things here contribute to what the amount of free energy of a system might be. Okay. So only processes, what we really need to worry about is that only processes with a negative change in Gibbs free energy are spontaneous. And spontaneous processes occur without energy input. And these are the ones that scientists want to understand. These are the ones that scientists want to know, because when you have these processes, these chemical reactions that occur without energy input, that energy will be released in these processes. Okay, so spontaneous processes will, generally speaking, release energy, and that energy that is released can actually be harnessed and used for cellular work. Okay, now this term spontaneous, it can be a tricky one. Oftentimes when we think of the term spontaneous as human beings, we think of, oh, that person's spontaneous. They'll go off and do whatever at the drop of a hat. They're going to go off and do this without even thinking about it. In very quick fashion, they're going to go off and spontaneously buy a car. We associate as human beings the term spontaneous with being fast or quick. But that is not what spontaneous means. Spontaneous means that it just happens. Okay? Spontaneous processes can occur either very, very quickly or very, very slowly. Okay, for instance, the breakdown of hydrogen peroxide into its constituent parts is a spontaneous process. If left to happen, it will just happen. It'll break down into its constituent parts. But it does not happen quickly. It happens very, very slowly. If you left out some hydrogen peroxide, it would break down, but it would take weeks, months, possibly even a year, okay, to do that, which is obviously not quick. There are ways that we can speed that breakdown up, but the idea is that spontaneous processes don't happen necessarily quickly. They can, but they just happen. And when they happen, they release free energy, okay? So for a process to occur without energy input, it must increase the entropy of the universe. So we think about that. Think about what hydrogen peroxide is, H2O2, okay? It would break down into water and, what's the other thing? Water and oxygen, okay? Water and oxygen. And if we look at whether or not this breakdown of hydrogen peroxide increases the entropy of the universe, let's think about it. We have one thing here. One thing is hydrogen peroxide. Okay, that's a 1 unit. Okay, once it breaks down, we have 2 units. We have water and oxygen. Okay, again, we start with one thing. When it breaks down, we have 2. Is that increasing the entropy of the universe? Is that increasing the disorder? I would say it is. We start with one thing and we end up with 2. When my kids want to increase the disorder at my house, I start with 1 kitchen plate and I end up with 5 pieces of that same kitchen plate. They have increased the disorder, okay? So that is an example of a spontaneous process. And as a result of the hydrogen peroxide breakdown, you don't have to put any energy in. In fact, you get energy out, okay? When you break these things down quickly, hydrogen peroxide breaking down very quickly, you can feel a test tube, and the test tube is actually hot, okay? And these spontaneous processes can be harnessed to perform work. The energy that these things tend to release can be harnessed to do work for the cell. And so that's why understanding this free energy idea is important, because when you have certain processes or chemical reactions that are spontaneous, they just happen, then you have energy that can be released and then harnessed to do work, okay? Now, free energy is a measure of a system's instability. In other words, its tendency to change to a more stable state. Now, this stuff we're going to talk about here is going to start to get a little bit confusing, and I'm going to try my best to make analogies that will help you understand it a little bit better. But during a spontaneous change, free energy decreases and the stability of a system increases. Okay, so take that into account. During a spontaneous change, the free energy decreases. In other words, we will get, let me draw on this real quick. In other words, if we are decreasing the free energy, we are getting this, okay? Negative change in free energy equals energy to do work. This is the important energy that we want to understand, that we want to know about, okay? This is energy to do work. When we see the Gibbs free energy sign with a negative in front of it, that tends to be good for a cell, because that means that there is energy floating around for the cell to do work. It's more complicated than that, but effectively that's kind of what happens, okay? And as a result, if the free energy decreases, if there is free energy that is released, if it is decreased, then the stability of the system should increase as well. The stability of the thing under study should increase as well, okay? A process is spontaneous and can perform work only when it is moving towards equilibrium or going downhill. And the reason this makes sense is because equilibrium is a state of maximum stability, okay? So these systems that release free energy oftentimes try to get to a state where they are more stable, okay? So let's I'm going to bring some examples into this, but I want to talk briefly about some other things first, okay? Movements away from equilibrium, movements away from stability are considered non-spontaneous, and they require the addition of energy from an outside source known as the surroundings. Okay, so let's talk about some of this stability, instability stuff and how it equates to equilibrium. All right, so I'm just gonna have you disregard that picture there for a minute. But these are two different systems here, in which we are going to talk about the release of free energy and the possibility of that free energy to be harnessed, okay? And the two examples that are shown here are diffusion and also a chemical reaction, okay? We'll expand on the chemical reaction example here after we get done talking about this, okay? So if we go back here, not that one. Yeah, this, okay. A process is spontaneous and can perform work when it is moving towards equilibrium. In other words, a process is spontaneous and can perform work when it is moving towards a state of stability. Okay? So when a system is trying to become stable, it will move to, let's see if I can get back in there. It will move to a state of maximum stability, and as a result of this, it will release free energy. Okay? So let's start here with diffusion. This diffusion example shows us a bunch of color molecules here. Okay, think of this as purple food coloring. Okay, you put a drop of purple food coloring in one spot in the water, and what do you notice happens very quickly? Very quickly, that drop spreads out, right? And the reason for that is because diffusion is happening. These molecules start in an area of high concentration, and they move to an area where it's more low concentration, like this water right here. That's low concentration of food dye. Those food dyes are going to move further away from each other, okay? So we can use this idea in terms of talking about stability, okay? Think about this. This is very apt right now. Think of these little molecules as people during a COVID pandemic. Right? They shouldn't be this close. When you are really close to somebody in a pandemic, or let's not go pandemic. Let's just talk about an elevator. Let's say we are in an elevator and we are packed in there to capacity. We got the most people in that elevator that we can have, right? That would represent what we see going on here with these food dyes, okay? Each one of those little food dyes would be like a person in an elevator. There is some instability there. Like, think about how you would feel in that elevator. You would feel like, I don't want to be by these people. They stink. That guy just farted, and that one smells bad, and that one's got too much perfume on. And it's just uncomfortable, right? Think of instability as uncomfortability in a small elevator packed with people. Okay, instability equals uncomfortable. Instability equals uncomfortable. And it's kind of the same for molecules and things of that nature as well. These things don't like being by each other. Okay, they're uncomfortable with each other. They're not stable. They don't feel like they're in this stable state. If they had feelings, they'd be like, get away from me. I'm in this crowded elevator by all these other gross purple molecules. And so naturally what they would want to do is they would want to reach a state of more stability. They would want to reach equilibrium. And so to achieve this state of comfortability for the molecules, they'll start to spread out, which is what we see happening right here. Okay? And so when molecules, or systems in this case, just generically, when systems work towards this state of equilibrium, they are going to release free energy. Okay, so if we could measure the amount of energy in this system during the diffusion of food coloring molecules throughout a glass of water, we could measure the amount of energy released. It would give us this negative value. We could measure energy released, and the way that would manifest in a lab is you could measure maybe the amount of heat produced. Okay, so it's going to be very minute. You wouldn't really notice. You'd have to have some really sensitive equipment. But if this were to happen and you could measure it at such a small measuring factor, you would measure a small amount of heat change in the liquid that we would see right here. The heat would technically go up because in this case we're releasing free energy. Okay? And when we release free energy, one of the side effects is the release of heat. Okay? So you would see a small heat release, okay? Moving from instability to more stability, equilibrium, which is what this represents here, is going to release free energy in the system. Now, this is free energy that could technically, if everything was right, could be harnessed by something that happens to live in that particular environment, okay? We apply this to a chemical reaction. This chemical reaction has a large compound here with a bunch of things packed next to each other, right? The same thing, same idea of people in an elevator. You've got each one of these little atoms here is maybe a person in the elevator, and they're all smashed next to each other. It's not necessarily super comfortable for this compound. It doesn't really like all that, okay? And so as a result, it wants to become more comfortable. It wants to reach this level of comfortability or stability. And so it's going to try to reach equilibrium. And the way that this particular chemical reaction does that is to basically break apart from its constituent parts. Okay. Again, it's very similar to that elevator one. All these things are smashed next to each other, and the elevator door opens. Oh my gosh, the elevator door opens, and they just get away from each other. They're away from the stinky guy or whatever. And so as a result of this return to comfortability or stability for this set of molecules here, energy is released, okay? And that energy, could be harnessed to do work by a cell, perhaps, all right? The breakdown of ATP is like this. Let me clear all this ink out of here. Okay, ATP, and I've done this before, adenosine, and then I'm going to use this special one here. Triphosphate. Okay, adenosine triphosphate is our energy molecule, right? And one of the reasons that it has this energy associated with it is because it crams all these negatively charged phosphates together. This is like taking three magnets that don't want to be next to each other and sticking them next to each other and making sure they stick there. They want to be away from each other. That is not comfortable for three magnets of the same pole to be next to each other the way that you see here. And as a result, there is some repelling forces that happen here. And when this thing releases its energy, it basically chops off a phosphate and attaches it to something else, okay, called phosphorylation. And it imparts that energy. There's an energy release here. And the organism can harness this energy and use it for what it needs, okay? And so this is akin, all of these negatively charged molecules being smashed together is like taking a spring that's already been stretched out and smashing it all next to each other and kind of holding it there. It wants to be unsprung, and you're holding it there. The minute you kind of let it go, it's going to go boing, and it'll pop out. And that's kind of what happens here. It releases a phosphate, and when this release of the phosphate is a return to stability for that molecule, okay? It releases some of that pent-up pressure. Now, this is something I did a while back, and it seems to kind of get the point across. Imagine yourself, and I'll do this. If you want to do this at home and maybe in private so you don't look silly, or if you want to just mess with your parents, you can do that too. Try to flex every muscle in your body at the exact same time. That's kind of what ATP is. All those phosphates bashed up next to each other. It's kind of like all of the muscles in the ATP are flexed at the same time. Or like all of these molecules smashed in together is almost like they're smashed in there, flexed together. So I'm going to try to do this, give you a wide angle view. And I don't know if it's going to work, but I'm going to look maybe kind of ridiculous. I'm going to try to flex all of the muscles in my upper body at the exact same time. I almost passed out. Okay. And when you do that, I almost blacked out. Anyway, when you do that, you're flexing everything in your body, and you're just really uncomfortable. It's like you're trying to hold all this stuff in there at the exact same time, and then you saw it just kind of let it go, just like, oh. I returned to stability when I did that. So I was very uncomfortable or unstable. I could not hold that massive, every muscle body flex for very long. I would feel very unstable. And when I let that go, I released it, I felt much more stable. And there would be, if I was a molecule, that would be akin to me releasing some of the energy that was kind of holding me together, okay? Or holding all those muscles tight, or holding all the molecules next to each other, okay? So that's kind of what is being talked about here. I hope that helps make a little bit more sense. And when I did that, I felt like, oh my gosh, I just released all this energy. That's not necessarily exactly how it worked, but that's kind of the idea, okay? So that's what's meant by this idea of free energy, stability, and equilibrium. These systems are, generally speaking, the ones that release free energy are in this state of instability, and they want to return to this state of stability or equilibrium, okay? Non-spontaneous processes are the ones that kind of go opposite. So for me to flex all the muscles in my body, I actually had to use a lot of energy. I had to put energy into myself, into my muscles, to make sure that I could hold that unstable conformation, okay? All right. Now, equilibrium, we got to relate here equilibrium to metabolism. Reactions in closed systems eventually reach equilibrium, and then they do not work. Cells are not in equilibrium. Okay, that's one thing we have to take into account here, is that cells are not in equilibrium. They are constantly working towards equilibrium because that's just the natural way of things. But cells are open systems, and they experience a constant flow of materials, including energy. A cell that reaches metabolic equilibrium is actually a dead cell. Okay, if there is no flow of anything, if there is only a reaching of this equilibrium, you've released your free energy, but then you don't get to really make any more, and you're dead, okay? The reason I talked about stability in systems and why systems reach equilibrium is because there are systems that happen in our cells, okay, chemical reactions and breakdown of molecules and things like that, that our cell can harness to utilize that free energy. But the cell itself, the second it starts to reach this equilibrium stage and not transfer new things into its body and move things through over and over, the minute it does this, it's going to be a dead cell. Okay? Metabolic disequilibrium is one of the defining features of life, in fact. Okay? So we can look at this analogy. This is a little hydroelectric system. A hydroelectric system that is closed looks like this, okay? Yes, for a time, maybe there's one system where you have the water in this cistern goes down, through gravity into this cistern and spins a little turbine and lights a light. There's a release of free energy. This is unstable. It is moving towards an area that is more stable, which we see here, which is a lower energy level. And on its way to that second cistern, it releases free energy to light the lamp, okay? Now that's great. We do release some free energy, but eventually the water levels are going to equal out here, and you can no longer spin the turbine. Whereas if you are looking at an open hydroelectric system, which this would be like our cell, we have a constant influx of new material, okay, the water, into this first cistern. It doesn't necessarily like this. It's unstable, so the water is going to move towards this second cistern. But instead of filling this second cistern up, it actually drains, okay? This is akin to us eating and us going pee or poo, right? In terms of large-scale, macro-scale organisms, right? And cells do the same thing. They take things in and they spit things out, okay? They go through endocytosis and exocytosis. And so there's this constant churning through of new materials. And as long as we get new materials and as long as we kick old materials out, we can continue the spinning of this free energy wheel. Okay? The system will constantly feel unstable, and it will constantly try to reach this level of stability, and we just won't let it. And that's a good thing, because when our cells are ultimately stable, they will ultimately die. Okay, now in our actual cells and in a lot of our different chemical pathways, metabolic pathways, we use multi-step systems, okay? And one of the things that we're going to talk about in Chapter 9 is this multi-step system where we release free energy in small increments. So it's not just something like this where it's one step. That's just to kind of illustrate how an organism is an open system. But when we're talking about these different catabolic pathways or pathways that release energy, oftentimes it's done in a series of chemical reactions. And when we talk about cell respiration in Chapter 9, we're going to talk about a series of 15 to 20 different small chemical reactions that are all kind of linked that release small amounts of free energy as the system flows. Okay. Now, one of the things that I want to talk about before we get done here are the two different types of chemical reactions. Okay, two different types of chemical reactions that are defined based on how they interact with this free energy. Okay. An exergonic reaction means that energy is exiting this chemical reaction. Okay, so the reaction proceeds with a net release of free energy, and it is spontaneous. Okay, and so these are chemical reactions where you could have a harnessing of that free energy that's released so that you could use it to do work. Okay, and so an example of this would be the breaking of glucose bonds. Okay, cell respiration. When we break the bonds of glucose, we can basically harness that energy. We turn it into ATP. And then we can use that energy somewhere else in our cell to do some work for us. Okay? The second type of chemical reaction is called an endergonic reaction, which means energy has to be put in. Ender, endo, into, ender, endo, into, ender, endo, into. Okay? All of those things mean into. Energy, in this case, energy into this system. Okay? So an endergonic reaction absorbs free energy from its surroundings, and it is considered non-spontaneous. Oftentimes, endergonic reactions are coupled with exergonic reactions, meaning the fuel or the energy that's released in an exergonic reaction can be used to drive endergonic reactions, and that's something that we see in our bodies. Okay, we see that happen in our bodies. It's very similar to coupling anabolic chemical pathways to catabolic chemical pathways. Okay, so here's a couple graphs that illustrate this phenomenon. This is a graph showing you the amount of energy associated with the reactants of a chemical reaction. Okay, so in this case, there's a large amount of energy associated with these reactants. And when these reactants turn into products, which we see happen right here in this chemical reaction, energy is released. Okay, and so we see here the amount of energy that is released. This shows us the total amount of energy that is released from the transition of these reactants into these products. And this tends to be a spontaneous process, and this energy can then be harnessed by our cells to do some work. Okay. The other one that we see here is the graph depicting what happens with an endergonic reaction, where we have reactants that tend to be have less energy associated with them. The bar here is much smaller. And if we want to get a product that tends to have more energy associated with it, we have to add that energy. And the example that was given in one of the previous slides was the production of glucose in plants by the process of photosynthesis. This energy comes from the sun. Okay, this energy here would come from the sun. The reactants that we would basically change into sugar are CO2 and water, right? And we add some of that energy from the sun, and we harness that energy from the sun, or the plants do, I should say. And as a result, we get this singular product, glucose, which has more energy associated with it than the originals, because we added energy from the sun. The plant added energy from the sun. Okay? Incidentally, you'll notice kind of what happens here. I'm going to draw again, just really quick. This will be the last thing we talk about. Okay. If we are thinking about, how this relates to the laws of thermodynamics, right? Specifically the second law of thermodynamics. A common rule of thumb, I guess you might say, is that reactants in an endergonic reaction tend to there tend to be more reactants. That's a H. There tend to be more reactants. There's one, two. There's two total reactants than there are products. C6H12O6. There is one product. Okay? And so this is an example of us being allowed to take something that is more disorganized and turning it into something that is more organized, being sugar. Okay? But to do this, we have to add energy. If we're allowed to do this, we have to add energy, and that energy is added from the sun. Contrary to the one I just showed you, let me take a picture of this one and draw on it. If we have the reactant, okay, C6H12O6, okay, that's one thing, and it breaks into the products of CO2 and H2O, which are the products of cell respiration. We notice that we end up with two things. We have increased the disorder. Okay, so this relates back to our kind of stipulations for spontaneous reactions. This will break down, okay, this will break down over time spontaneously to two different things. For that to occur, it has to increase the disorder of the universe, and it has. We started with one thing, and we end up with two things, okay? So as a result, we've increased the disorder, and we've got some energy back, okay? So that's how that kind of relates to the idea of the second law of thermodynamics, which we had already talked about, okay? All right, the last video will kind of put it all together and talk about how we can make these chemical reactions happen much more quickly with the use of something known as enzymes. And so we've seen enzymes mentioned a lot. We've talked a lot about enzymes. We've talked a lot about proteins. And in section 4 here, we're going to get into some pretty good specifics about how these enzymes help to speed up these chemical reactions. All right, so I'll see you then.